Hey, hello and welcome to Woven Chemistry. I'm Gene Weaver, and in this video we're going to talk about thermochemistry. This video builds upon the previous one where we discussed and built a pretty good foundation of these topics right here that are fundamental to thermochemistry. If you haven't watched it, I really recommend you go back and watch that before we do this video where we're going to work on making graphs. Now, as is the case with all of my videos, I really encourage you to stop the video and answer my questions. I say that because after 20-some years of teaching chemistry, I've learned that one of the hardest things about chemistry is that students don't know how to think and apply their knowledge. The point of my videos is to give you a chance to think. And there's no penalty. Nobody's going to know if you get stuff wrong. But if you just watch my videos, your takeaway is going to be to remember. Remembering is not the key to chemistry. You need to learn how to think. Okay, enough said on that. Let's move on to the first slide. Okay, so just like in part one, we've got an ice cube sitting on the counter in your house. It's negative 20 degrees Celsius. So what I'd like you to do is sketch a graph of temperature versus time for what happens to this ice cube as it sits there, but before it starts to melt. Okay, details are important in your graph. Okay, pause the video and come on back when you're finished. So the graph will look something like this. Temperature will start at minus 20 and it will rise to 0. It's probably not going to rise linearly, but let's just keep it simple and keep it linear. Okay, so next question. Now that it's at 0 degrees, it's melting. So I'd like you to sketch another graph of what happens to the temperature of the ice cube as it melts. Okay, this is what we're going to get. The temperature's at 0, and because it's undergoing a phase change, the heat that is flowing into the ice cube does not go to raise its temperature. It goes to help those particles overcome the IMFs, and so the temperature stays constant. Okay, next, third question. Now that it's all liquid, I'd like you to sketch one last graph of temperature versus time for what happens next to this liquid 0-degree water. Okay, and we start at 0 and the temperature is going to go up to 20, the temperature of our room. It stops changing at 20 because at that point there's no more temperature gradient between the air and the water, so there's no more heat flow, temperature stays constant. So this next graph, I've taken all three of those previous graphs and brought them into one. So what I'd like you to do now is sketch this graph on your paper and then answer these three questions on your graph. Okay, details matter here, so take a few minutes, pause the video, and see if you can get all of the details perfect. So as we label the graph, we've got solid and we have liquid, and when the temperature is flat, we've got a phase change, solid to liquid. When the temperature changes at the macroscopic level, that means we have a kinetic energy change at the microscopic level. When the temperature is flat, and when the phase changes, that means we've got a change in potential energy. Since kinetic energy equals 1/2 mv squared, v for velocity, in these kinetic energy segments, the particles are changing their velocity. In the potential energy segment, that heat is going to the particles to overcome their IMFs. Okay, now let's get a little quantitative. Let's take the same scenario, but let's say that ice cube is 30 grams, and I'd like you to get out your calculator and calculate how much heat that ice cube absorbs as it goes from minus 20 Celsius to 20 degrees Celsius water. Okay, to help you out, here are the equations that you're going to need to use for the first and third segment. That's what you're going to want to use for the middle segment, and here are the constants. Okay, one last thing, I'd like you to label these portions of the graph. Okay, so indicate how much heat it takes to get to this point, and this point. So Q1 would be calculated like this. Q2 for the warming of the water is calculated like this. And then that delta H, we're going to take those 30 grams, convert it to moles, use that molar heat of fusion in joules per mole, and we get 10,017. If we add all of those up, we get 13,755, which is the total heat. That's what corresponds to this third box, 13,755. The first box is the amount of energy it takes to warm the liquid, which is this number. The middle box is a little bit different because this box is not just this 1017, it's the 1017 plus the 1230. Okay, and we get 11,247. Okay, put away your calculator. Next question is conceptual. How would this graph change if the ice cube was 60 grams instead of 30 grams? How would it change? With twice the mass, it'll take twice the amount of heat. And so each of these red numbers is double what it was on the previous graph. Okay, and here are our calculations from the previous graph. But instead of using 30 grams in each of those calculations, we'll use 60. One more conceptual question. Why is the solid segment, so this segment, steeper than the liquid segment? Okay, hopefully this is challenging you a little bit. Pause the video and think a bit about this one. See what you can come up with. So if we think about the slope of the line represents degrees Celsius per joule. So that means how much the temperature changes for each joule of energy. If we look at the specific heat, we see that water needs twice as many joules to change its temperature as the ice does. Well, in our scenario, the ice and the water are changing 20 degrees, but the water needs more heat. So this distance from here to here needs to be more than this distance. So that explains why this slope is shallower than this one. Okay, last question. This kind of brings it all together. Now we've got an ice cube in a beaker and it's being warmed by a Bunsen burner. I'd like you to sketch a graph of temperature versus heat for this sample. So let's make some assumptions. The water gets warm enough to boil, but evaporation does not occur. Let's also assume the water vapor stays contained so that the sample can reach 130 degrees Celsius. And lastly, I would like you to incorporate into the graph the fact that the molar heat of vaporization is greater than the molar heat of fusion. Okay, label all of these points, and remember, details matter. See if you can nail all of them. So the graph should look something like this. We're going to have two plateaus because there will be two phase changes. We'll have melting on the first one and boiling on the next one. Now, this enthalpy of vaporization is quite a bit more than the enthalpy of fusion. So that's going to mean that this line is going to be longer because it's going to take more heat to boil the water than it will to melt the water. Okay, remember when the temperature changes, the kinetic energy will go up at the microscopic level. When we have a phase change at the macroscopic level, we have a potential energy change at the microscopic. Kinetic energy corresponds to a change in particle velocity. Potential energy in this case will correspond to a change in IMFs. And that wraps up this video. So what I've done in actually these two videos is I've presented a number of different concepts that apply to thermal chemistry, and we've looked at them through a lot of different angles, and hopefully in the whole process your knowledge has been stretched and you're ending up with a much greater, more substantial understanding of these principles. And remember, we've also looked at these through the lenses of macroscopic, microscopic, and symbolic. Hopefully all of this stuff has allowed you to weave these concepts of thermochemistry much more tightly in your mind, and your next test on this goes much better. Okay, once again, thanks for joining me, and I hope to see you again.